Welcome back. You are running a course on classification, part 2. In part 1, we saw 4 classifiers, and in part 2 also we have seen a number of classifiers. Okay, and this is part of the machine learning course conducted by Suburaj Academy, and we are learning using Python 3 language. Other option is using R, but Python is very popular for machine learning. We are lesson 5. So 4 lessons we already seen in part 2, classification. And in this lesson we are going to focus on ensemble learning concerning boosting. The last lesson also we looked at ensemble learning, but no technique was adopted, no strategy was adopted. But here we are going to use a boosting strategy. No, we did use some strategy, bootstrap strategy, but here we are going to adopt boosting strategy. So boosting is a powerful machine learning technique like bootstrap. Bootstrap is a good technique. It combines multiple weak or base learners to create a strong predictive model. See, we know that when you try to model a data for classification, some of the training examples may be weak. Okay, we have to convert them into strong training example. That's what is boosting is. So, boosting belongs to a family of ensemble methods. It aims to improve the overall performance of a learning algorithm by combining the predictions of several methods. So, here again, we are going to do several models. We are going to have model number of times. We use the same algorithm, but we model it number of times. That's ensemble A. The fundamental idea is to iteratively train a series of weak models. The weak models are also known as base learners, in such a way that each subsequent model focuses on correcting the mistakes made by its predecessors. It's not really a mistake. You get an error with some examples. So that will be corrected so that overall accuracy improves. This iterative process allows boosting to gradually increase the predictive accuracy of the final model. Boosting algorithms work by assigning weights to each training instance. Boosting algorithms, they work by assigning weights to each training instance with initially equal weights. In each iteration, the boosting algorithm trains the base learner on the training data and then adjusts the weights of the instances based on the errors. So suppose the model is making, suppose the training example is causing more error, then those examples are given more weight. Initially, all the training examples are given equal weight. Instances that are misclassified by the current model are given higher weights to make them more influential in the subsequent build rather. This way, subsequent base learners may pay more attention to the previously misclassified instances, effectively boosting their importance. The final prediction of the boost model obtained by aggregating the prediction of all the base learners. So, we have to aggregate the results of all the builds, okay? Typically using weighted voting scheme, where the weights are proportional to the performance of each base learner or each build. So there are two popular algorithms. One is AdaBoost, and the other is gradient boost. AdaBoost stands for adaptive boosting. It's one technique. It is one of the first successful boosting algorithms introduced in late 1990s. So AdaBoost assigns more weight to misclassified instances and less weight to correctly classified instances, ensuring that subsequent base learners focus on difficult instances. Another well-known boosting algorithm is gradient boost. So it optimizes the loss function using gradient descent and sequentially adds base learners to minimize loss. It adds base learners to minimize loss. So two different techniques. One is it gives different weights. The weaker build is given more weight, and a good build is given less weight, weaker instance. Whereas in the gradient boost, the loss function is used, and you get a residual, right? The residual is progressively reduced. Boosting has been widely used in various domains, including classification, regression, ranking problems. The effective situation when the data is complex and the base learners are simple, such as decision trees or shallow neural networks. Boosting algorithms have demonstrated outstanding performance in many real-world situations and have won numerous machine learning competitions. The strategy combines multiple weak classifiers into a single strong classifier. So, in fact, whatever you do is not wasted, it's aggregated. Whenever you do a classification, whether weak or strong, and that data is taken into account for arriving at the final classification. Classification algorithms such as naive Bayes decision tree can be chosen for boosting. Boosting builds multiple classifiers in a sequential manner. So when you do the bootstrap and other methods, we were using parallelly, we were doing it. But here we do sequentially. We build multiple classifiers in a sequential manner. Boosting builds the initial classifier giving equal weights to each sample and then focuses on correctly classifying misclassified training example in subsequent bits. So AdaBoost assigns weights to each training example. First time the weights of all examples will be equal. After AdaBoost increases the weight for misqualified ones so that they get higher probability for selection in the training set, expecting that next classifier will learn to classify correctly. This is the hope. If you more weight, we hope that you get it give lesser error. After each classifier is trained, the classifier weight is computed based on accuracy. So for ranking also, the accuracy, the classifier is given a weight, each classifier is given a weight that depends on the accuracy it gets. So a poor accuracy classifier will have lesser importance or lesser role in the final classification. So we are talking final classification. So the final prediction is based on the weighted sum of all classifiers. That's why the rank of the weight of a poor qualifier will be less, so it will not contribute much to the output. We got by formula fxi sin k is equal to 1 to k alpha fk xi, where k is total number of classifiers. Fk xi is the output of weak classifier, and each classifier k for the input features at xi. Xi is the training example, and the fk is the output of the classifier. And alpha k is the weight applied to classifier k and is given by alpha k is equal to 1 by 2 log natural 1 minus epsilon k by epsilon k. See, so the finally is aggregation. You have you sum all. The alpha k is the weight applied and it's also learning rate, and it's multiplied by the output, and the sign is also important. So alpha k is based on the classifier error rate epsilon k, which is the number of misqualified records over the training set divided by the total number of records of the training set. So it's basically error. The final output value f of xi is just a linear combination of all weak classifiers, and final decision depends on the sign or the sum. So this is how you get the final. So once you have the final prediction, then a new data, unforeseen data, can be classified using the formula or using the classification. So SQL supports AdaBoost. The base estimator from which ensemble is built should have capability to utilize differential weight of samples. All classifiers won't permit given differential weights to the weights of samples. So the best classifier suitable for AdaBoost is decision tree and naive bias. N estimator is nothing but maximum number of estimators at which boosting algorithm is terminated. Default is 50. Learning rate, it shrinks the contribution of each classifier by the learning rate. You saw alpha. There's always a trade-off between N estimators and learning rate. So these are the three key parameters of AdaBoost classifier. So now look at the second important algorithm for boosting called gradient boosting. Gradient boosting calculates the residuals from previous classifier, attempts to reduce it in the next bit. They will always reduce it, but try to reduce it. Once it reaches a stage in which residuals do not have any pattern, it stops modeling residuals. Use of gradient descent algorithm in each stage to minimize errors. Gradient boosting uses decision tree as a base classifier. In fact, you need not specify any classifier when you are using gradient boosting algorithm. The steps are: fit the model to the data, y is equal to f1x. Okay, fit the next model to the residuals. What is f3x? Is equal to y minus f1x. Y is the actual value, f1x is the estimated value, y minus f1x is the residual. So you next fit the next model to residual, and you keep doing this. Repeat the above until residuals do not change appreciably. The final model can be written sigma I is equal to 1 to k, alpha k, fk xi, where alpha is the learning rate or accuracy of model k. So you have to import SQL and ensemble gradient boosting classifier, and it takes the following parameters: n estimators, max depth, and max features. Max features are number of features to consider when looking for a best split. Max depth, maximum depth limits the number of levels from root. Maximum depth limit from the number of levels from the root. And n estimators, number of times you build it. Okay. So what we have seen so far is what is boosting, and two different types of boosting: AdaBoost and gradient boosting. Now I will show you the examples, solved examples, and I'll show you 4 solved examples implemented using the Jupyter notebook. So this is AdaBoost, So import the same libraries. I'm going to use social network ads. You are familiar with the dataset as a data frame. So age and estimated salary determines whether a person purchased the SUV or car. Okay. So assign age and estimated salary for X and purchase for Y. Split data set into test and train. So now here is the classification. Here you have to specify which classifier you are going to use, base classifier. So I'm going to use decision tree classifier. SQL and tree, import decision tree classifier. Then SQL and ensemble, import AdaBoost classifier. So these two are important statements. And you first create a decision tree classifier with Gini as the splitting criterion. Decision tree classifier, criterion Gini. So first you create a decision tree classifier, and that you use it dec CLF in the AdaBoost classifier. Ada CLF is AdaBoost classifier, dec CL using dictionary classifier. You can also use naive Bayes. N estimate is equal to 50. 50 builds will make, and then fit the classifier X train, Y train, and predict the labels for the test data. The predict the Y predictor is Ada CLF dot predict X test, so that we can find out how good was the fit. Now I can make a confusion matrix for this. Yeah, it is 69 by 80, 0.8625 is the accuracy of the algorithm AdaBoost for the data social network as for whether the customer churn or not. Done. Now we'll repeat the same example, same algorithm for another data set. That's our popular data set, the IRI data set. You will get a better accuracy. Okay, do all this. I import libraries, assign data frame. Okay, then you assign also the X and Y, and split the data set, training and test set. Then this is not AdaBoost. Yeah, you need to have another classifier specified. For gradient boost, you don't require any other classifier, but here you require the scalar tree import dictionary classifier, then the base classifier, then ensemble import AdaBoost classifier, create a dictionary classifier object, use that object to find out in the AdaBoost classifier, fit it, and predict the Y values corresponding to test data. Now we can build a confusion matrix. You get a very good accuracy of 1, right? You got an accuracy of 1. That's because the data is very good, really. So to summarize AdaBoost, you need to have another classifier, either dictionary or naive Bayes, to do the classification, and based on that's for the classification. Use that in the AdaBoost classification. Now we'll go to the gradient boost. Gradient boost is, as I told you, is an excellent algorithm for boosting. So let's take the same social network. You the data frame assigned, X value is assigned, splitting, testing and training. So here you don't need any other classifier. So straight away scalar ensemble import gradient boosting classifier. This is not required. So gradient CLF, gradient boosting classifier, estimated 500. It assumes dictionary as the underlying classifier. Max depth is 10. So you do this, you get its foot. You can find the confusion matrix. So you get 0.8625. And gradient boost also, it doesn't improve the accuracy of the social network ads. Okay, but the next algorithm, next implementation of gradient boost, I have done with the IRI data set. So naturally, you can expect a good accuracy. So this is gradient boost 2. Import all libraries, assign the data frame, churn, iris, I'm sorry, I've said iris here, so but that will be, yeah, this is a customer churn. Gradient boost 2 is customer churn. If you use iris, you'll definitely get a better result. Let's see what happens to. We were already getting less accuracy for customer chain. Let us see what happens when you use ensemble, when you use AdaBoost classifier. You get 0.91. It was 0.86 earlier, or no, it was 0.91 you get, or 0.92 you get. So you can, if you want to change, you can try with any data set. I haven't done it with the iris. If I do it with iris, I'll get 1 as the accuracy. So with this, we have completed this. We took 2 examples of AdaBoost and then 2 examples of AdaBoost. So go through the slides again and again. Experiment these programs in your computer and get confidence that the boosting algorithms definitely help in improving the accuracy of classification. Okay, that's all for now. Until we meet again. Bye bye.